This is my lab report, Lab 3 Black Hole and Orbits. The purpose of this lab was to explore how Newton's law and momentum principle can be applied to orbital motion. In part 1, I analyzed the motion of a star to estimate the mass of the black hole it orbits. In part 2, I simulated a spaceship affected by both a planet and a moon and adjusted its launch velocity to create a stable figure 8 orbit. Here's a quick preview of my results. I estimated the mass of the black hole to be approximately 1.27 times to the 10 to the 34 kilograms. For part 2, I found that the initial takeoff velocity of negative 30,000 meters per second gave me the best figure 8 orbit result. In this lab, everything ties back to Newton's second law and the law of universal gravitation. I used the equation F net equals dp over dt equals m delta v over delta t to calculate the net force acting on the star in part 1, based on changes in its momentum. The gravitational force gm1 times m2 divided by r squared allowed me to work backward and estimate the mass of the black hole from that force. In part 2, I used these same principles to find the correct launch velocity for the spaceship. By simulating the combined gravitational pull from the planet and moon, I adjusted the velocity to avoid crashes and keep the motion influenced by both bodies. For part 1, I analyzed the star's trajectory using GlowScript. The star has a known mass and time interval. I loop through the velocity data and compute the star's initial and final momentum. Then I calculate the change in momentum over time to get net force using Newton's second law. I split the net force into parallel and perpendicular components. Using the perpendicular force, I estimate the black hole's mass with a gravitational formula. Finally, I update the star's position and draw arrows for net force and its components. This repeats through the loop, giving me a set of black hole mass estimates that I later averaged. Using the gravitational force formula and rearranging it to solve for the black hole's mass, I averaged all the values from my loop to get a final estimate of 1.27 times 10 to the 34. In part 2, the goal was to find the right velocity so the ship orbits both bodies in a figure 8 without crashing into either. I calculate the moon's orbital speed and set its initial velocity. Then I gave the spaceship a starting velocity of negative 30,000 meters per second to try and create a figure 8 orbit. The main loop runs the simulation forward in time. I calculate gravitational forces on the moon from the planet and spaceship. Using Newton's second law, I update the velocities and position of both objects. Lastly, I add the current position to the trail to draw the figure 8 path. By adjusting the launch velocity, I found a path that loops around both to the planet and the moon. After testing multiple velocities, I found that an initial velocity of negative 30,000 meters per second gave me a stable orbit where the ship loops around both bodies. While this lab was computational, I compared my predicted black hole mass to real-world black hole types. This value is far larger than a stellar mass black hole. There are several possible sources of error. A large time step could reduce accuracy, and the model assumes no air resistance. Also, the simulation is sensitive to the exact initial velocity, and rounding errors in force calculation can compound over time. In part 1, the system is the star, and in part 2, it's a spaceship. Everything else, the black hole, planet, and moon, are surroundings that exert gravitational forces. For the first question, the components of net force and momentum change point in the same directions, but they found differently. Net force is calculated by summing external forces acting on an object, like gravity from nearby masses. On the other hand, the rate of change of momentum comes directly from an object's own velocity and mass. A key insight is that the parallel component of the force affects how fast the object moves, while the perpendicular components alter its direction, which we clearly saw in the star's orbital path. To predict the full system's movement, I have to model every gravitational interaction: the black hole, star, planet, and moon. This means tracking their masses, distance, and initial velocities. In terms of dominance, the black hole and the star would have the strongest gravitational pull due to their massive size. The planet and moon would be more influenced than influencing, especially the moon, which is the lightest and most sensitive to gravitational changes from all directions.